Okay, so welcome everyone to the main talk today. And it's my pleasure to introduce Kevin Aguyar Brix from the University of Southern Denmark in Odense, who's going to talk to us about covers of dynamical systems.
Thank you, and thanks for showing up, and thanks for inviting me. I'm very happy to be here. Just telling Tristan that I've been here once, but that was for a school trip many years ago, so it's different to be here now. Thanks to Akila for introducing the topic. In fact, I'd say the essence of what I'm trying to say was already in what we just heard. So many of the things I'll say again, but that's maybe all right. The point is to take, for me, a dynamical system that we might be interested in, but maybe it's not as well behaved as we'd like. And then a cover is an attempt to build something that looks like it, but it's slightly better, with better properties. So it's more well behaved, but it looks like the original thing. And then hopefully they're so tightly connected that you can study this nicer thing and infer something about the original thing you're interested in. So I should say there's many faces I don't know, and I don't know your backgrounds. The talk will be about dynamical systems, topological dynamical systems. And my own background is in operator algebras and C-star algebras. So there's a hidden, not so hidden motivation coming from C-star algebras doing this. But that's not an essential part. What we tried to do here was to keep it fully in the language of dynamics. And I want to mention this is joint work with Xin Li, who's a professor in Glasgow, and then Jeremy Hume, who's actually just finishing his PhD now under Xin Li. So we met in Glasgow, and just want to mention that he's currently finishing. He's a very strong mathematician with many good ideas. So he's very strong, yeah. So we started talking about these things. We all had an interest in dynamics, and what we're trying to do is take as general a class of dynamical system that we're interested in, and then see if we can build a cover that's nicer. And what I want to try to explain is what nicer means. And one motivation for being nicer is that it's amenable to C-star algebraic techniques. And that's not essential, but it's sort of in the background. So something I've come to appreciate more with time is the usefulness of a role model. And the role model in this case is shifts of finite type. So let me first start by, I want to talk about shifts of finite type that we just heard about, but from a slightly different perspective. And then I want to give you just some guiding examples. We try to really be, in the paper where we wrote up these things, we tried to have many examples, but I'll focus on two that sort of exemplify what the key issues are. So I'll talk about these examples, and then I'll talk about our construction of a cover, which is very tightly connected to these Krieger and Fischer covers that we just heard about. And then maybe some perspectives in the end. So the role model is really shifts of finite type, and so we just saw what that is. So I'll spend a few minutes hopefully convincing you why this is a good role model. And it's true that you can picture them. So you saw the formal definition, the original definition in terms of these finite forbidden blocks. So let me just jump to the pictures. They're sort of easier for me to draw. So one example is, I don't think you had this, but the full shift is this example of a graph. It's the full shift because there's no obstruction. If I go along any edge, there's no obstruction to which other edge I can go along. So everything is allowed with these two symbols. But you could also have something like this. So this one is the full shift. And this one, we did see the golden mean. And this is really because these dynamical systems have an entropy associated with them, and the entropy in this case is the golden mean, pops up there. You could also have something maybe slightly more degenerate like this, where you just have a single loop you can walk along. So it gives you different examples, and the C-star algebras you can associate to this. So for the people among you that are interested in C-star algebras, what you get, for example, here is Kunz algebra Kunz algebra O2. In fact, that's also what you get here, but that takes a bit more work to see. And here you get the circle. So far everything agrees with what we just heard, but I want to emphasize actually that what I mean is one-sided SFTs. So here I mean I'm interested in right infinite sequences. So I have a starting point, and then I only go to the infinite in the one direction. And it turns out that dynamicists have much more studied the bi-infinite case. So it makes perfect sense to start with that. But if you come from a C-star algebraic motivation, this seems slightly more natural to do. So it's exactly as we just saw, except I don't look at the bi-infinite strings, I look at right infinite strings. And then again, there's a shift, which is just exactly the same thing, but now because I have a starting point, x naught, x1, x2, and so on, what the shift does is just forget about the first letter. So it shifts to the left, just like we saw before, but now it just removes that first bit. But what's important is that this is not a homeomorphism now as it was before, because before all the information, you just translate back and forth, so all the information is preserved. But now I'm actually throwing away some information, so I can't expect this to be injective. I can't expect it to be what's the word? Invertible. So, but it is as nice as it gets, still being not invertible. And this whole thing that we're trying to do is for non-invertible dynamical systems. So it is a local homeomorphism. That means that for every point, I can restrict to an open subset on which it is a homeomorphism. So that's locally, it's a homeomorphism. It means that as a map, it is open, and also that it's locally injected. That's just what this means to be. So this is as nice as it gets when it's not invertible. And it's even nicer than that. It's what's called positively expansive. Or this is another nice property. So expansive means, maybe I won't write down the precise definition, but the picture you should have in mind is that no matter any 2 points I take that are close to each other, it doesn't matter how close, but they should be distinct. If I then apply this map, at some point they'll get far away. So the intuition is maybe not the first time, but at least after some finite number of steps, they will get far apart along this shift map. And positive because I'm only shifting in the natural numbers direction. So it's a local homeomorphism. It's positively expansive. And these path spaces, they are totally disconnected compact metric spaces. So that's the path spaces here. Usually they're Cantor sets, but you could have isolated points when you draw more complicated graphs. But in general, they're totally disconnected compact metric spaces. And there's actually an abstract theorem that tells you that if you do have positively expansive local homeomorphism on a totally disconnected compact metric space, then it is a shift of finite type. So there's some universality happening here. So this is a good class of examples to start with. Good. So there's the initial part of having a dynamical system I'm interested in, and all the ideas basically come from all the nice properties that we have here. But the input the next part of the input that I want to emphasize is what's called a transfer operator. So this is now going into, this is purely dynamics, and this is now going into a more functional analytic aspect. So let's call this left shift sigma. That's what you usually do. So the transfer operator associated with this different notations in the literature, let me just use lambda here. This is an operator now on L infinity of x. On L infinity of x. So it takes functions, bounded functions, to other bounded functions. And what it does is it tries to remedy the fact that this is not invertible. But it can't do that because it's not invertible. So what it can do is that it inverts it up to an averaging. That's the idea. So explicitly what you do is you take a function here and you want to evaluate it at a point, and then you want to just evaluate f on the inverse, the preimage under the action. But there's more than one preimage point, so what you want to do is sum over the inverse and then y, and then evaluate that function on all the preimages. So this is the best you can do if you try to invert this map. Turns out this map has a ton of information about the original thing, so it's a super important thing. I think the story is that it comes from physics, thermodynamic formalism, Ruel's study of equilibrium states and these things, but it's super relevant for this even if you don't care about that other stuff. So you can always do this, and this I'll return to this, and then I want to add one more ingredient to it, but something that's trivial now but will not be trivial for the examples where things fail. And that is, I want to add a weight, suggestively call it W. And in this case, the weight is just constantly 1, so nothing is happening. But I'll return to this bit. And the reason why this is important is that this will be where I can change things. When I'm trying to make the case that this is the good example. In a few minutes, we'll talk about the not so good examples. Things are not maybe as nice, but this is where I can change things. And part of the thing that's nice here is that it's not immediate, but you can check this. It's defined on all the bounded functions. And you can see that this thing is bounded as well, because this is finite to 1. But in fact, it has this even nicer property of sending continuous functions into continuous functions. This is the important point. So just for a shorthand, this is what we'll call a continuous transfer operator. When I say that the transfer operator is continuous, I don't mean that it's continuous as an operator. I mean that it respects continuous functions. Because things are set up like this, I could also say that I have a continuous weight. By that, I just mean a choice of such a function. It doesn't have to be constantly 1, but a choice so that it respects this. You could imagine choosing something else here. Okay. So this is a particularly nice property. And I guess if you're not already convinced that it's nice, at least for the C-star algebraically minded people, you should know that this kind of property is exactly what you need to build a C-star algebra from such dynamical systems. Either if you're interested in groupoid C-star algebras, the reason why a Haar system allows you to build groupoid C-star algebras is exactly because encoded in the definition of a Haar system is a property that they should define something that takes continuous functions to continuous functions. Or alternatively, there's these things called topological quivers, which are graphs, as we've seen, but now in a topological version. So both vertices and edges allowed to be topological sets, and range and source maps are allowed to be continuous functions. But for a topological quiver, you require an open range map. And the reason why you require an open range map is because then there exists such weights that will give you this property. And then you can build C-star correspondence. And then a C-star algebra from that C-star correspondence. So this is just to say these two maybe most fundamental ways of building C-star algebras from dynamical systems both require this kind of property. So this hopefully motivates the reason why when in a minute we'll give you 2 examples where this fails, you might want to see if you can change that so you can get this property. So this is really the property that we're looking for. You can always, basically always, do something like this, but this is not automatic. This is the important bit. One motivation comes from C star functions. But it turns out that there are other nice properties, reasons why this is relevant. So before I move on to these other examples, are there questions to this so far?
The X is still the shift or could it be any
You can always define this, but what I'm trying to emphasize is that for SFTs, things work out nicely. Yes. So I'll only consider examples where you always have this kind of situation. And then this is the extra thing that you have for shifts of finite type, but you don't have it for the things, the two examples I'll give you now.
this kind of situation?
You can always do that for the examples I'll talk about, yes. But you cannot always expect this. Okay, so maybe I'll be a bit brief here. So that one of the examples is suffix shifts. And specifically, so the canonical example is the even shift. So let me draw it again. And maybe just to clarify, the reason why this does present the even shift is because if you imagine having a 1 and later having a 1 again, you can only have an even number of zeros here. You go around. So this is canonical picture of the even shift. And in fact, maybe let me add this. Let me add this slightly bigger graph here. Okay, so again, because there are some things that are easier to see when I look at the one-sided things, the right infinite things instead of the invertible cases. So one thing to see is that the shift now, so the shift is now not a local homeomorphism. It acts as exactly the same way, but now this is still positively expansive. So this actually positive expansive actually implies locally injective. So locally injective, it means what the word says. So for every point, you can find an open neighborhood so that when you restrict the map, it's injective. But that's not the same as being a local homeomorphism because it might not map that open thing to an open thing. And in fact, this one fails to be open.
Expensive, then it would have to be even just injected. Like,
No, locally injective.
I thought it was you have two points that are distinct and you keep mapping them by the map and they eventually get far apart.
Yes, at some point they'll get far apart.
But if there were even 2 points which were not, if it wasn't injected on 2 points mapping to the same point, then you could never get far apart from them.
I'm not sure I follow.
So you have 2 points that are distinct, but your mapping is not injective everywhere. So the 2 points happen to map to the same.
Right.
Then they could never get far apart.
But then they have to be, if that happens, they would have to be further than the, so being positively expansive has a uniform distance.
Okay, so there exists a neighborhood of points as all 2 points within that neighborhood.
Well, so let me see if I understood what you said. You're saying that it is possible, and of course that's true, it is possible to take 2 distinct points so they both shift to the same thing.
Yeah.
Right. But expansivity tells you that if this is the case, then these two will have to be further than this global distance apart. So they're trivially far away because you don't have to shift to see that they're far away.
Okay.
So positive expansivity only implies local injection, but it doesn't imply openness. And if you want, maybe let me not do the construction or the full details, but if you want to check this, you can look at, for example, the cylinder set of 1. So that's just all the right infinite sequences that start with 1. And then you apply the shift. This is one of the basic open sets. So if this were open, this would have to be open. This thing consists of all elements that start with 1. So for example, this thing is allowed. So the shift here would contain the 0, only zeros, but no neighborhood. You can check this, no neighborhood of 0 is contained in there. So it means that image set is not open. I haven't given you the details, but this is what you can check if you're curious. So here's an example where I'm trying to push that local homeomorphisms are really the nice situation. This is an example where one of the properties hold, but the other one doesn't. And this means actually now, so there's a theorem that says from this suffix shift, you can still build this thing given like this, but there's a theorem usually called Blanchett's theorem that tells you that in this setting, you can find these weights so that this happens if and only if your map is open. So you can't find these weights so that this property is always the case. So the transfer operator does not have this property. So there's no continuous transfer. Okay, so that's one example, and I'll return to the examples when we've seen the construction and then see a possible way of resolving this problem. So the other example is from what is it called? Piecewise. Piecewise linear maps or piecewise invertible maps. And maybe let me just give you one example. This is a tent map. Maybe you've seen this before. This is just the picture of a tent. Like this. So this seemingly innocuous system here is causing troubles if you look in functional analytic direction. How am I doing on time? Okay. It turns out if you look at this, that this is, so this is called the tent map. This is actually an open map. But it's not locally injective. Something we should okay. Good. So there's a large class of piecewise invertible maps, piecewise linear maps. You can sort of imagine you can construct them similarly to this, but this is really one of the base case, this tent map. This one fails to be open, but it is locally injective. This one is open, but it fails to be locally injective. And you'll see that because every point here in the domain has 2 preimages. Sorry, every point here has 2 preimages, but exactly at a half, you have a single preimage. So no matter what open set I take around this, there'll be 2 in every point away from a half, and there'll be a single one at a half. So it's not locally injective at a half, because no open set, you can't, no matter how you restrict this map on an open neighborhood around a half, it's not injective. Right, so here you can consider open neighborhood around a half. If you want to check that. And then you can, again, you can build this transfer operator. So let's call the tent map T. So for the transfer operator, I'm claiming that, so it's open, and then if you believe this Blanchett theorem, it means that there is a set of weights so that you have this nice property with continuous functions. But the canonical choice is always just to choose weights equal to 1. So let me try to show you that if I take the constant function 1 and I evaluate it at a point, and this point is not 1, then by definition, just like what the transfer operator is, it takes the average over the pre-images. So I want to show you that this transfer operator is not continuous. The constant function 1, that's a continuous function. But if I evaluate this at the point x that's not 1, this is just constantly 1. And I told you that this is constantly 1 because that's the natural choice of weight. Then for any point that's away from 1, there's exactly 2 pre-images. So this will be 2. Because there's exactly 2 pre-images and each carries weight 1. But then if I do the same thing at 1, there's exactly a single pre-image, namely the weight at a half. So that's 1. So this function now is constantly 2 unless you reach the endpoint in which it's 1. So this is not continuous. So the canonical choice of just choosing this thing will not make it work. Yeah.
The sum that defines the transfer operator, for a shifted finite type, it's a finite sum?
All these sums will be finite because these are, you mean when I evaluate at a point?
Yeah.
Yeah, because these maps are finite to 1. Yeah. So I've not said that explicitly, but in order for this to make sense, you want this to be finite to 1, or at least locally finite to 1. And there are more general ways of expressing this. I'm trying to be not too technical, just saying that there's this weight that hopefully makes more intuitive sense, that you can weight your elements. Okay, so this is sort of silly, right? That it's very easy to draw a system. It should be able to work because it's open, but then you make this canonical choice and it's just at a single point it fails, right? So it's sort of almost there, but it's not there. But you could also imagine what the fix would be, right? You could imagine that if you're allowed to choose a different weight, then maybe you could change this value here, and maybe it would be all right. And spoiler is that's exactly what happens. And of course, people have realized that you can do this. I think our contribution just says that there is a reason for being able to do this. Good. So I tried to tell you that the nice case example is the shifts of finite type, and then 2 examples that fail in 2 different ways, where what you get is not what you want. You can always build a transfer operator, but it's not continuous in that right sense.
In this case, I think just say the way exactly the half is 2 way that you're asking.
Yes. Yes. So this weight doesn't have to be continuous as a function on the point. But that's a bit ad hoc to just postulate that. And maybe if the example is more complicated, then you wouldn't know what to do. Okay, so maybe I'll jump to part 3 and tell you something about construction. So the promise now is that there is a way to not go all the way up to the nice case of shifts of finite type, but at least to remedy these problems in many instances. That's the promise. So one way to think about this is that there is a machine, and what you do is you give it an input, it does something, and then it spits out an output. So I'll try to explain those 3 steps. So the input is, as you might expect, some kind of dynamical system like this, and it's not as nice as we'd like it to be. So you should have some continuous map. What else do I want? So I want it to be finite degree. So by this, I really just mean that it's finite to 1, or at least if it's not on compact space, then locally it should be finite to 1. There are ways of getting around this, but this will make this picture make this picture work. Well, if you're only on a locally compact space, then I think the right way to think of it is to fix any compact set, and then look at the pre-images intersected with that compact set should be finite. Yeah. But now I'm just assuming all the spaces are compact, so I don't need to worry about that. So it should have this, but I also need some transfer operator because, or a choice of weight. So plus, I guess, a transfer operator associated with this map. And I guess if you get this and you check that it already has this nice property, well, then you're happy, then you don't need to do anything. But the issue is when that's not the case, and now you've seen a few examples where it's not the case. So let me just be explicit here and say it's given like this for some choice of weight like this. Okay, so the machine is a recursive procedure. So it proceeds in countably many steps. Somehow, the issue is you look at your transfer operator, it goes here, right? And you want it to take continuous into continuous. So then you start asking, okay, let's take the continuous functions. Where do I land? If I don't land in the continuous functions, then I take that image and I generate something new, get a new transfer operator, and then I see where that takes the continuous functions. Maybe it's not fixed yet. Do it again, do it again. And in principle, I need to do this infinitely many times. So it's like let's say a recursive. Can you see from the screen actually? Yeah. Okay. So there's a recursive definition. So let me just write it down and then I'll mostly focus on what the output is. So the 0 level just takes those functions I'm interested in. But the nth step takes something generated by those functions, but also the image of the previous step. And then the pre-images, the induced maps from T. So T is a nice function on compact Hausdorff space. So it gives you, by Gelfand duality, you get an operator T star. And really what you want to do is look at the star algebra generated by this or the closure. It doesn't matter much. It's just to say in each step you generate something from the original thing, whatever the transfer operator contributes with and whatever the original map contributes with. And then let's just say B is the union of all these. Closed off. Everything is happening within bounded operators. So this is commutative. So it means that it's functions on some space. And this is the space we want. So now maybe I can fit it in here. The output, actually maybe I'll, okay. I'll draw it here and then. The input is the system I'm interested in with this choice of weight or this transfer operator. The output is now my original space. But now the spectrum of this B algebra I just constructed. And if you go through the construction, you'll see that the space generates a space, the map generates a map, and in fact, it generates factor map. Just like Aquila said, the factor map is just a surjective continuous function that intertwines the action. So in this case, t and t hat. So you get this canonical space x hat, which arises as a spectrum of this procedure. And going through the construction, you automatically also get canonical factor maps going down onto the original thing, as well as an induced dynamical system, t hat. And the important observation is that t hat is nice. Otherwise, there'd be no point in this. T hat is always open. If you test it on, maybe, I'll get back to what happens in those examples. But it's always open. But in general, it need not be locally injective. So it's not necessarily a local homeomorphism. We don't get all the way back to the niceties of that. But at least we get to something open. The reason why that's good is because there's a theorem now that tells us then there exists a choice of weight that makes this happen. So you get this, and you get, let's say, continuous weights. So there's this procedure. It has this output. And then, okay, so I put it all the way down. But point is that the output is really nice. The map is really nice. And moreover, it has a universal property. It's the smallest thing with these nice properties.
So okay, you've got your B0, then you're adding in all these extra functions, some of which may not be continuous or give a star out generated by this. So
yeah.
So these are all functions on X until the very end when you say, okay, now I've got a star output, so I can look at this spectrum of this thing, which is
yes.
Okay.
But this is all still happening. So B, curly B, is still in L infinity of X. But X hat is now, I mean, in principle, an abstract space.
So would it be the same as maybe looking at the what? I can't remember, it's the initial topology, the path topology, the best topology which makes all the functions in B squiggly thing continuous. Then that will give you a new topology on the original space X.
And then you close off.
And then you take the subject about factorification, I guess.
Well, it's not the biggest thing, it's the smallest thing. I imagine that you'd get some maximal property if you do that.
But I thought
I'm not sure.
Okay, but yeah, okay.
But there's definitely some way of okay, so this is a functional analytic description. You do these algebras, basically star algebras, and then you close it off to get a C star algebra, you get a spectrum. You can also do it from the bottom up. So the way you do it more concretely is that you take the space X and now the measures on that space, satisfying some properties, and then elements in each step. So each Bn will give you an Xn. They're also commutative. And in each step, it's pairs of points in the original space with some measures. So I don't know if this answers your question, but there is a way of doing it from the original space and then doing this procedure from the bottom up. It's more obvious than I've indicated. And really, the point is just that in each step, I'm taking this into account. So in the end, I'll have T star will map C of X hat into C of X hat. So by duality, I'll get T hat on that space. So it's Gelfand duality once you keep track of what's going on. Yeah. Okay, other questions?
Wait. So you okay, it's not continuous, but is it Borel thing?
As a function. I don't know. I actually wouldn't well. I don't know. I don't know. What we need is that it's we need some properties that it's, for example, bounded above and bounded away from zero. That will give you nice properties of the transfer operator. But I actually don't know with the more measure theoretic properties. And so maybe let me jump to this example first because it's easy to say. The W hat exactly fixes this issue here. So the W hat will have speed 2. So maybe just say one word that there's a slight subtlety that maybe I'll just say in a few words, is that X actually sits inside of X hat. There's a canonical inclusion. Pi is a canonical continuous factor map going down. And pi is really what tells you that the new thing remembers something of the original thing. But when you go through the construction, you'll also see that there is a function going from the original thing into the new thing. And this function has dense image, but it's not continuous. It's continuous on some large chunk, but it's not continuous everywhere. So it's a section to the map pi. So somehow the new thing is constructed from the old thing. It sits in there in some obscure way. So in this case, if you do this construction here and you do this thing, then what you need is the original space. This is just the interval here. But you need what you get when this X hat actually blows up this point, this treble point a half. So really it blows up and adds the whole orbit to that. And that's not really what we want. So I won't go into the details here, but there's an essential, we call it the essential cover. Which in many cases is the one you'd really like because it's the one that makes more intuitive sense. So the X hat here will take the original thing and then just blow up this point. But the essential thing will remove all that thing you blew up and just keep that original point, but with the new weight. So in this case, the essential is exactly the same space, but what it changes is the weight. It changes the operator. And so we call the first one, we call the minimal, and the second one we call the essential. And it turns out that if you go back to here, maybe you remember that there was a Krieger cover and there was a Fischer cover. And that's exactly the analogy here. So the Krieger cover, this is our minimal cover. Or I should say we recover this. This is an old, very nice thing. And then the Fischer cover, this is what we call, or what we get when we do the essential construction, then we recover the Fischer cover. Yes. It's minimal in the sense of, so that's a good point. It's minimal in the sense of our universal property. That if I have another space with these nice properties that also has factor maps going down, dense inclusions going up, then that factor map will factor through X hat. So X hat is the smallest one. And essential is smaller, just like the Fischer cover is smaller. But just like for the Fischer cover, you mentioned that as well, you need, and this doesn't always exist. You need a slightly nicer thing for this to exist. It always, when it exists, it always sits inside the Krieger cover. Well, because it's because they're two slightly different universal properties. So in the Fischer cover, you take like a dense G delta, and the iota map is now continuous. But now it's only not defined on the whole thing. So there's just a slight subtlety I didn't want to go too much into. Not the same, it has its own universal property. But the analogy is that the minimal cover corresponds to the Krieger cover, and you said it's a bit confusing, and I agree, but the good thing about it is it always exists. You can always build it. This thing has nicer properties, but it doesn't always exist. You need irreducible. And then in this particular case, you see it that the minimal one blows up this point, but the essential one removes that blow up and just keeps the original space. Okay. So maybe I want to mention that. So in my PhD, these are very well-known constructions. So what I tried to do, did some work with Toke Carlsen, is that we would take general subshifts now given by any forbidden set. You can define a cover, but now these things are not so good because they're sort of built for finite things, and sophic means finite, and this is reflected in these graphs being finite. But for general so there's uncountably many subshifts, but there's only countably many sophics. So most of them are not sophic. And in that case, we had an old construction of Toke and that we studied and used to build C-star algebras and groupoids and these things. And we built it from the bottom up in a concrete way, but we didn't suspected that it had a universal property, but we didn't really know. So for me, this is also nice because this sort of goes back to my PhD work, where this is now a very general construction. It has a universal property that sort of explains why things work. So it works even for general subshifts that are not sophic like that. But then it also works for something like piecewise linear maps. And then maybe I don't have much more space on the board. Maybe I can just say that if, for those of you who are interested in groupoids, SFTs will give you nice étale groupoids. If you care about groupoids, you're always happy if it's étale, things are easier to work with. But there's this notion of being semi-étale. In an étale, the range and source maps are local homeomorphisms. But for a semi-étale, they're only locally injective. So not open necessarily, but only locally injective. That's what's called semi-étale. And none of these constructions that I put here, like the usual groupoid construction, doesn't work because a Haar system would force structure maps to be open. And that's exactly not the case. So you can't use these constructions, but Klaus Thomsen made a way of building C-star algebra from the semi-étale groupoid. And it turns out that our framework actually applies here. So our framework doesn't just work for graphs or for maps, it actually works for topological graphs, where you have two maps instead of a single map. And then a groupoid is a particular example of that. So if you apply our construction in that semi-étale case, you get an étale groupoid cover. So there's, I guess, just want to say, so we recover this thing that Klaus Thomsen did, but in a way that has a universal property, for example. So it's just to say that there's a lot of flexibility in this kind of construction. And so maybe I'm running out of time, so maybe this last word will be that, so this work is only for dynamical systems, but sort of we're hoping that now we set it up so that people interested maybe in C-star algebras or other topics could take it from here, and if you're interested in a system, maybe you can build this cover that has nicer properties, work with that, and then see how much you can get back for the original thing. That's sort of the idea. So for example, you can build C-star algebras from this. And so we do study a few of these things. One thing is in this construction, I said it's recursive, and you do this B0, Bn, take the union here. And in general, it's an infinite procedure. But in the happy case that it's a finite procedure, it turns out that even more is preserved. So something like expansivity is preserved when this thing terminates after finitely many steps. So you might be interested in asking, when does that happen? Actually, suffix shifts are examples of that. They are exactly the shifts that have that property. And this ties in with, I think you mentioned this, that what defines them is also that they have these only finitely many follower sets. That's the same, it's the same property that's reflected in this thing terminating after finitely many steps. So this has consequences for thermodynamic formalism that I don't know much about, but you can transfer properties from the cover down to the original thing. That's the point. So might be interesting to study, have better understanding of when this thing terminates after finally many steps, because then they're even closer, more closely related. Good. I think that's what I want to say, and I'm happy to take any more questions if you have.
Thank you very nice talk. Any questions?
So this definition with the recursive one.
Yeah.
So what you want in the end, like the important thing is that the t-hat is open, right?
Yes. Yes. We want that the t-hat is open, and then these either the new transfer operator or these weighted new weights.
Mm-hmm. And is there some intuition behind the construction? And is there then some way of, like, why would you expect to get something open if you do this?
Right. Yeah, I'm not sure what to point to. So what we did was sort of in steps that we were inspired by what happened for general subshifts, and actually using these follower sets, so the opposites, the predecessor sets, and so these steps we take here correspond to taking these predecessor sets or future sets, and it works for general subshifts, and then it's Blanchard's theorem, but I'm not sure how much intuition that gives. Because so Blanchard, I didn't write it, but I mentioned hopefully that that's the theorem that tells you that these weights exist exactly if the map is open. So there's these two ways of viewing it. So once you check that in the construction you get transfer operator having this nice property, then the map is open. So that's why we'd expect it. But I'm not sure I can tell you like a topological reason why that happens.
Okay, thank you.
If your system XT has some property like I don't know, some sort of shadowing or specification, does this lift to the cover?
Right. So that's one of the things we can show that when this thing terminates in finite and many steps. You need that extra thing. So shadowing is one thing, and topological transitivity, this kind of thing. So there's the whole thermodynamic formalism that will work when, yeah.
Cool. Right,
Yeah.
thanks.
No, anyone online? Let's see. No, doesn't look like it.
Okay.
Okay, well, in that case, let's thank the speaker again.